Oscillations with damping. We have problem here with a uniform rod, mass M and length L. And it is free to oscillate about this point here at time t equals 0. We give it an impulse, and as a result, at time t equals 0, it would have an angular velocity which is big omega 0. And then at any time after that, it starts oscillating from one side to another. We have damping in the system, and let's say from drag, and that is given by minus b times the velocity, which is the angular velocity, which is given by theta dot, which is a function of time. And what we want to do is to be able to predict the motion at any moment in time. So we want to solve this problem. First, we want to translate it into a mathematical formulation, as we did before, and then solve that formulation, and then we are able to predict the position at any moment in time. Because we have a rotation here, we assume that this is the direction, so the outward direction is the positive rotation. The solution, we start with the force diagram. We need the momentum of inertia. You can get that from books. It's 1/3 ml squared. The force diagram, we have the force from gravity, but we have also the drag force. Now obviously we would have a torque acting on the system here, and we choose it about, as we did before, about this point here. So we end up with two elements of the torque, one from gravity and the other one from the drag. It could be from air, or if it's inside a liquid, it could be the medium. So the next thing we need to do is to write the equation of motion. That is theta double dot. That is the alpha is the angular acceleration, which is equal to tau over I. Now tau has two components. One is gravity, and the other one is the drag. Okay, we know theta here at any moment in time. So for the gravity term, we can write, that would be a restoring force, so it's going to be minus mg times sine theta times L over 2. That's the force times the length. And we have the drag. That would be a minus b theta dot. Divided by I can already write it here. This is 1/3 ml squared. If we take omega 0 squared as 3g over L, you're going to see why I'm doing this shortly. And we denote gamma equal by b divided by I. And we make an assumption, small angular approximation, so sine theta equals theta. Now if we substitute all these back, we end up with a differential equation. Going to bring everything to this side. See, we lose the m here, and you end up with that. You lose one L, you have G, theta, and you have 3/2, and you have one L down there. And the 3G/L is omega 0 squared. Same thing here. We'll have B over I, so this is all I, and that's given by gamma, so we'll have minus gamma theta. It's going to be with a plus sign, plus gamma theta dot, and this will also be with a plus sign, omega 0 squared, right? Times theta equals 0. I think I'm missing a 2 here. This m cancels, so we have G, L, L cancels, G, theta, should have a 2 here, should be a 2 here. So this is the differential equation, and we have the initial conditions. We know that theta dot at time t equals 0 equals big omega 0, and theta itself at time t equals 0 is 0. So at this point we have a full mathematical description of the physical problem. Now we solve the equations. Okay, we solve the equations. Start with one case, which is overdamping. So the damping is strong in the system, and that's the case when gamma squared is larger than 4 omega 0 squared. Solution theta t is of this form: a e to the power minus some alpha 1t plus b e to minus alpha 2 times t. So theta dot would be minus alpha 1a e minus alpha 1t minus alpha 2b e minus alpha 2t. And alpha 1 is gamma minus square root of gamma squared minus 4 omega 0 squared divided by 2, and alpha 2, let me write them together, so it's alpha 1 and 2 will be minus and plus. Okay, we make use of the initial condition theta equals 0 at time t equals 0, and that gives theta equals 0 when this is 0, so this is 1 and this is 1 at time t equals 0, so A would be equal to minus B. We make use of the second condition now, theta dot at 0 equals omega 0. Okay, so this is, the exponent is 1 here and here. We have a minus A1A. Remember that A is minus V. So minus minus alpha 1A plus alpha 2A. And that is equal to omega 0. So this gives A, which is omega 0 divided by alpha 2 minus alpha 1. And B would be minus that. So finally, now we can write that theta t is equal to omega 0 over alpha 2 minus alpha 1 e to the power minus alpha 1t minus e to the power minus alpha 2t. This is the solution of the system. Let's make a sketch. This is omega 0 here. This is t. Sketches for theta. So you have two decaying exponents. Let's start from here. There's one. There's another one. And the solution is the one minus the other one. You can do this in red. This is the combined solution. It would be something like this. So this is how the system would behave in the case of overdamping. All right, now let's look at the case of underdamping. So if the damping is weak, the solution will have a different form. Just like this. Theta of t, e, a times e minus gamma over 2 times t. It is decaying, exponentially decaying in time, but there is also an oscillatory term, cosine omega t plus 5. And this omega here is the square root of 4 omega 0 squared minus gamma squared divided by 2. Okay, so the damping now is small. Okay, so we do as before. Let's take the derivative, give us minus gamma over 2a e times, let me put that inside, So we have AE minus gamma over 2 times T, and inside here we'll have a minus gamma over 2 cosine omega t plus phi. So the first term times this. Now we take the derivative of the second term, we're going to have a minus omega times sine omega t plus phi. Alright, so when theta is at t equals 0, theta is 0. This is theta, so it would be 0 when t is 0, this would be 1, this would be 0, we have a cosine phi equals 0. So from here a cosine phi equals 0. Now a cannot be 0, that's the amplitude. So we conclude that phi is pi over 2. And the other condition, initial condition, is the angular velocity is big omega 0. Now let's look here. So you substitute 0, that is 1. This is, we know that this is 0 now because at 0 this would be cosine phi, and phi is pi half, so this term is gone. So we end up with a times minus omega, right? And this would give us 1. So this gives a to 0 equals a times minus omega. Or in other words, a equals to omega minus omega 0 over omega. So the full solution now for this case, the underdamping, would be theta t a full solution. We had it here. See this here? So theta t a. Now we know a, which is a minus omega 0 over omega times e to the power minus gamma over 2 times t cosine omega t plus a phi. We know phi, but instead of that I could have it like that, right? I can also replace that by the whole thing by a minus sign. So it's going to be a plus sine omega t. And it would look like this. You see that there? Yeah. This is theta. This is the time. The exponential decay would be this envelope here. And in let me do it in blue now. In blue would be this whole thing. It's going to be oscillating and decaying.